Yeah, okay, good. So now, and of course, this is the vector at each time instance, and this guy is the scalar, right? And somehow last time I learned to, but it doesn't work anymore. I've learned to highlight better the this way maybe, yeah, yeah. So this guy is a scalar, okay? So but no, not anymore. Oh, horrible thing. It's horrible, horrible. Anyway, S sub I is a scalar and G sub I are the vectors, right? And these vectors are the topographies, okay? So, and Dasha must have sent you the video about the SVD, right? What singular value decomposition is, right? And it was describing to you how to, let's say, take a matrix A and represent it as a product of three matrices where U and V would be orthogonal matrices and S would be a diagonal matrix. Okay. And so what's important when we talk about SVD is that the matrix U, the columns of matrix U form the basis. Basically, you can think of this as basis for the column space of A, okay? And columns of V form the basis of the row space of A, okay? So if you take matrix A and it has like certain columns and certain rows, and there are many of them, but you want to somehow represent these vectors in some nice basis, then you can take few elements of vector U or of matrix U, few columns of matrix U, and few columns of vector of matrix V, and describe the rows and the columns of the matrix A. This sounds abstract, I understand, but I will now try to show you some specific examples with actually our data, how we generate them when we generate the data with one source, with two sources, and etc. So that you have some intuition behind it, okay? And then we will switch to something simpler. We switch to very simple dipole fitting task where we have only one dipole producing our data, and then we will develop from there, and at some point we'll arrive to the SVD thing, and therefore I think we will talk about it right now so that you have it in your mind and it's somehow you get assimilated to this idea, okay? You get accustomed to this idea, okay? So you assimilate the idea, yeah. So let me try and show you. I always say when it concerns Zoom and stuff, always say try. Okay, so I'll stop sharing this guy for a moment, and then I will share with you my screen, my laptop screen. Okay, okay, share screen. Yes, all right. And then I have MATLAB launched there. Okay, so very nice. So, so let me try and generate some data for you. Okay, this is the script in MATLAB, which I mean, I'm not insistent you understand this because it may be unnecessarily complicated. But the good idea about the script is that it actually goes to the very guts and starts from the very first principles, and then and then generates all this stuff. Okay, so unfortunately, this year I'm using the computer that has graphical card that is not very well designed to work with MATLAB, and therefore it's very, very slow. The rotations and things are very slow. But let's assume here that we have a dipole somewhere here in the head, yeah, and we generate just the time series, just the matrix of these time series. Okay, so G is our topography, okay? G is our topography vector. Size of G is 102 sensors by 1. Okay, this is just a column vector. Okay, and we have some activation time series vector S, and if we plot, if we close all and then plot vector S, for instance, we will get this kind of activation profile. Okay, so on the x-axis it's the time samples, and on y-axis is the activity of this of this only source. Okay, and then what we do, we will simply generate the data by multiplying the topography of this source by the time course. Okay, so it will be since S in MATLAB here we have 1 by 101, so it's a row vector. We multiply it by the vector which is of size 102 by 1, and then if you multiply this by that, you get a matrix, right? Let's call it x0, that is of the size 102 sensors by 101 time point, which we will be able to plot, right? If we do this, okay. So this is something you probably already seen with Dasha. So you basically have 102 traces of different color. Each color corresponds to a channel. Yeah, there's another way, and there is another way to visualize this matrix is to use image scale command and then add color bar to it so that you understand what I will be showing to you now. Okay, so no, this is not what I meant. All right, So you can basically see that this is the same thing, but just displayed differently. Each row here, each line is a channel. The intensity of the channel is color coded. So if you have blue, it's negative something. If you have yellow, it's positive something, right? And you know, many of them are close to zero. So this is our matrix, okay? This matrix is very special, right? This matrix has rank 1. Rank of this matrix is 1, meaning that exactly that it can be represented by a single product of one column vector multiplied by another column vector. Okay, but if you imagine that this situation happens in real life and you observe something like this, which sometimes it's what we observe is kind of close to this, okay, then you may be interested in actually finding the this main vector which represents, which describes the columns of this matrix, and another main vector which describes the rows of this matrix, right? Of course, in this case, every column is just a scaled version of vector G, right? And every row of this matrix is just a scaled version of vector S, right? So if I take, for instance, because it's all scale free, it plots it in a scale free manner, right? And so if I plot, for instance, for you x0, whatever, I don't know, 10, I will get this, right? And if I plot for you x, I don't know, 24, I don't know why, but it's just 24, I will get exactly the same thing. Okay, so it will be exactly the same, except that the scale in terms of shape, but the magnitude may be different, but the shape is exactly the same, right? So it means that if I plot for you x0 divided by the norm, somehow normalize it, right? 24, and then if I ask to hold on, and I will plot, let's say 10, and I will plot it with dots, right? So that we can see. I will get exactly the same two columns, right? The same is true for the rows, right? But if I now assume that in this matrix I add some noise to it, right? Let's say like we do it here, right? X noisy is equal to x0 plus some amount of noise to it, right? Then if we plot this xn, then we will get something like this, right? And of course, things are also quite simple, but now the rows and the columns are of course not identical copies of each other, although they're pretty similar, right? And you want some statistics, you want something which summarizes for you the main column and the main row of this matrix. Okay, to do that, you can use SVD. Okay, this is a practical application of single value decomposition. So what you do, you say that I will call it UUSSVV, In Python, you have exactly the same thing, except that you have to write np every time, and then import np first. Well, but this is Python. It's not as bad as Samsung, but it's also had its own good sides. Okay, let's put it this way. So you put it, you do it this way, and then see the interesting thing is that since the matrix xn is of the size 102 by 101, matrix U will have meaningful will have 102 by 102 elements, and matrix VV will have 101 100 by 1 dimension, right? But only in our case, only the first column of U and the first column of VV are meaningful. Okay, to see this, let's do this. I'm always using close all so that I can, when I plot, I can see. Let's do image scale these matrices. Okay, let's do image scale. Let's first do image scale VV. Okay, and then prime because it's columns, but because it's about temporal dimension, I just do the transpose. Okay, you can't see very well, but this guy. Let me first plot only first. First, let's say 20 columns. Okay. Yeah, now you can see better. So see, these guys, the rows in this plot are the columns of VV, right? Because I transposed it before I plotted, right? But the reason I transposed it because I wanted to, because VV speaks about the rows of matrix X, right? And therefore rows go this way, right? Therefore I transposed it, right? Because it's our time dimension. Okay, but the very first guy looks terribly similar to our source, right? And that's in fact our source. That's the time series of our source for a rank 1 matrix or rank wide matrix plus noise. Okay, this approximates the time series of our source very well. If I, for instance, compute the correlation coefficient between V1 and what was that? And it was S, right? I get 0.9997 correlation. So they're pretty much identical, right? And if we go back to our cosine between the two vectors, right, notation, then we can always do this, right? We can always do this, but before I do that, I have to divide it by the norm of S, right? Because vector S is not unit norm, but VV, its columns are unit norm vectors by definition of SVD, by the properties. Okay, so I get basically this correlation, as I already mentioned to you, right? Correlation is exactly the cosine between the two sequences, right? And now if I plot it on another figure, plot VV, you can see that it's exactly, well, with some a little bit of noise, of course, but it's exactly the shape of the time series. Of course, the scale is different. If I now use plot S here, then of course you will not you will have difficulties in comparing them because it doesn't observe the scale. The norm of vector of this right singular vector, what is called, and on the left singular, has to be unity. It has to be one. Therefore, if you sum up all the elements of this blue guy, they will give you one. And raise it to the square and take the square root of it, you get one. If you sum up these guys, there is no such restriction. Therefore, but the shape is exactly the same, right? So basically, look, the right singular vector of the data matrix xn, see here, this is this matrix xn. I will again show you in the of this matrix, the right singular vector tells you about the temporal structure present in this matrix. Okay, because if this matrix was completely noisy matrix, then your first singular vectors would also be very noisy, and you wouldn't see any structure, any smoothness, nothing. Okay, you probably will play with this in your homework at some point, and we'll give it to you with Dasha. But yeah, now the same thing, because the same thing can be told about can be said about the columns, right? For the situation when we have a rank 1 matrix, The first column of U, first column of U is equivalent, or in terms of shape, right, is equivalent to the uh, uh, to the uh, to the topography of our source. See, this was the topography of our source, right? And this is very important, right? Because in this very simple case, and we can actually try to experiment with this. Let's put it 1.5, for instance, okay? Put 1.5, we put more noise. And now we again visualize our data first. See, now they're noisier, right? Quite noisy, right? But then you can then again do SVD, right? And then you again look, sorry, at correlation coefficient. You get, well, of course, slightly less, but still pretty high, right? Very, very, very high agreement between the actual forward model that was used to generate the source, actual topography of the source, and what we got from the data using the mathematical manipulation, right? And the same thing we can do with I transpose it because S is rho, right? Therefore, I transpose it to MATLAB because it's not pure Python. Python would understand it, but better would be if it didn't. But okay, so and then we have another, we have this correlation also pretty high, right? So and then we can also try. Let's do it 5.5. Okay, let's do it 5.5, and then again plot our matrix. Okay, you can barely see, well, of course you can see, but it resembles this test at the ophthalmologist, right? When you need to see the digits and whatever. So you can see, of course, the structure, but very vaguely. And then you can, sorry, there's something wrong. Let's close it. Yeah, and then let's do again SVD of n, and then let's again measure the correlation coefficient. Still, pretty high, right? And then again UU and G. Okay, we get pretty high correlation coefficients, and if we simply compare these vectors by plotting the normalized versions, right? UU is normalized anyhow, and then you hold on and you plot your vector G divided by norm of G, right? Then you can compare them, and you can see that they're pretty much the same, right? The peaks are there. And you remember that this is a topography, right? This is something that we will plot today in a nicely color-coded way. But just to show you just the simple values of activity of electrodes due to the source, basically, right? Due to the single source, they will be distributed like this across electrodes. Some electrodes would have negative activation values, right? Some electrodes will have high positive activation, and many of them will be close to zero, right? Okay, now another thing. But how do I know how many dipoles are in my data? Okay, for this, in the SVD, you have this matrix S, which basically a diagonal matrix that scales contributions of the columns of these products. You see what happens basically. UU times SS times VV is your matrix XN. Let's make it XN1, right? It's exactly this matrix, okay? So you can approximate this matrix. It's exactly this matrix, and it comprises these products, basically U1 multiplied by S11 multiplied by VV1 transpose plus the second guy, right? I'm just simply expanding this product, this USV transpose product, right? And of course, I had to put transpose the XN1, I had to put VV transpose, okay? So my bad. So here, and then plus 3 and etc. Okay, until the rank until 101, until the smallest value of the number of rows and columns, right? Okay, so and let's call it x approximate. You will see why I call it x approximate. It's hold on. Why? Of course, I called it SS, not to confuse it with the source time series. Okay, so let's close all and plot XA prime. Okay, this is my XA prime. Okay, and let's try to represent XA prime using only the first element of the SVD. Okay, again, close all, plot XA prime. I have something like this. Looks a bit ugly because it's rank 1 thing, but it recovers you the source and its activity very nicely, if as compared to if you plot the data, the noisy data, the original noisy data. So if you put these two or next to each other, then you can see how nicely the use of SVD, left and right singular vectors, how nicely it allows you to highlight the activity of the source and suppress this noise that is present all around, right? See? So now, how do you know, and how did I know that I needed to take only the first outer product, right, and ignore the rest, right? Well, as I already mentioned, the matrix S tells you about this. Okay, so if you again let's again visualize it, matrix S. Okay, matrix SS. Okay, and let's again visualize only the first, let's say 20 elements, because then you can see it better. See? Okay, and then add color bar to it. Color bar. So you can see that if you look, this is the diagonal matrix, meaning that its all diagonal elements are 0, and you have only the main diagonal values that are non-zero, and the very first diagonal value is very high, right, as compared to the rest. We usually, when we will work with this matrix, we will usually be plotting not the rest of the matrix, but we will be plotting only the diagonal of this matrix, and I use stem to plot this diagonal. It just makes a nice plot. Sorry, what the again, yeah, I make mistakes all the time. Stem SS, yeah, okay. This is stem. This is only the diagonal of this S matrix, and we see that the first guy sticks out, and the rest of the guys are much lower, right, in amplitude, right? That tells you that there is one main dimension, one main frame, if you will, okay, in your matrix, and the rest are not important, okay? Of course, you can add a lot of noise, and then this guy and this guy will come close to each other, and SVD will be helpless, right? It won't be able to. But SVD otherwise is a very, very powerful thing, okay? So if SVD fails, then it means you have really, really too much of noise in your data, okay? And that's why the SVD or its counterpart in the world of symmetric matrices called eigenvalue decomposition, that's why they're often used to denoise the data. Okay, but that's not the main use of those, right? The main use in our business is that we use SVD in order to recover the bones, if you will, okay, the elements of the bones of your data, okay, the main vectors that your vector can be described with, okay. And this was the situation with a single dipole, right? When we had a single dipole and single source, right? Let us see what happens if we have let's say 2 dipoles, okay? So very similar story. You can see my screen very well, right? So this SI is J, so you can see it,
Yes.
right? Okay, good. So so let's generate the 2 source time series, okay? And now I will close all, and I will plot SI, and then I will do hold on, and I will plot SJ, okay? So Of course, this is an artificial example. I'm just, making this example basically. Okay, so you have these two time series, which are poorly decaying sinusoidal oscillations. Okay, and the first source is active with this time series, and the second source is active with this time series. Okay, and we have the topographies of these two sources, which are stored in the matrix G orthogonal, and they columns I's columns and JJ's columns. Okay, in order to make things look exactly the same as before, let's make it this way. Okay, I and sorry, Control V, GJ, GJ, and then let's make it GI plus GJ. Okay, so now plot x0 prime. Okay, now this is a time series of our data. We can maybe, if you want them to look something like a little bit more interesting, let's do it this way. Because otherwise they look, yeah, decay a little bit more. Okay, so decay this time more, a little bit more physiological. Okay, so but you can see the difference already, right, between the previous data where we had the all time series intersected in one point, right? Because of course they are rank one, right? They're scaled versions of each other. If something passes through zero, regardless of how you scale it, the other one will also pass through zero, right? Here, of course, you have a mixture of two sources, and the sources are active differently with the shift in time, and therefore you have a more interesting structure in your data, right? And then, of course, you can add noise to it. You can plot now the noisy time series. Here, how they look. Okay, this is a reasonable amount of noise. This is usually how much you have in ARP data. This is, I mean, sometimes they're cleaner, sometimes they're less clean, but this is on average. But the problem is that in the ERP data, you have also noise which has spatial structure, which we're not working with now. At this point, we're not working with it. Okay, but so just white noise, the simplest noise we can have. I mean, it doesn't have any structure. Therefore, if the data is something that has a structure, then you can extract it. Okay, and the noise is just doesn't have any spatial, neither temporal, no spatial structure. Okay, so now to see the structure, let's apply SVD again. You again do SVD of matrix xn, and then let's first plot close all, sorry, then stem diag of SS. Okay, we immediately see that now we have two sources. Okay, these two guys stick out because we have two-dimensional structure in our matrix. Okay, so it's basically it's one column vector multiplied by a row vector plus another column vector multiplied by another row vector, right? And some noise. Okay, but since the noise doesn't have any spatial structure, it cannot be described by yet another vector multiplied by yet another time series, right? Therefore, we see only the two which stick out, and the rest are spread out. Okay, so basically, let me give you an analogy. You probably already heard about Fourier decomposition. Okay, it's like in Fourier decomposition, you basically take your data and you decompose it into a set of sinusoids and cosinusoids, right? And you try to sum your data with these guys, right? And create your data as a superposition of these sines and cosines with different amplitudes, right? And these amplitudes are the spectrum, right? Well, not the spectrum, but well, you can call it spectrum. Okay. By the way, the values that we just plotted, these guys, it's also called a spectrum, but it's a spectrum of the matrix. Okay, and this is not a random coincidence. In just Fourier transform, your spectrum is fixed. your basis vector, not spectrum, your basis vectors are fixed. Your basis vectors are always cosines and sines, okay? And you always measure the similarity of your data with respect to these cosines and sines, okay? When you deal with matrices and do it this way, you use SVD or whatever, you extract the basis from the matrix itself. So you find the basis vectors in such a way that the first basis vectors, which you order them in the order. So the first are the most important one. The second one is the second most important one, and etc. Right? Importance means the amount of power, the amount of variance, the amount of changes in the matrix that project onto this basis vector. Okay, so this projection basically is what you measure, and this power of this projection is actually the spectrum. But the difference with Fourier is that in the Fourier domain, in the Fourier analysis, it's called harmonic analysis, right? The bases are harmonic functions, comprises harmonic functions. But in matrix analysis using SVD as we do it here, right? The basis comes from the data, it comes from the matrix. So it's, if you will, it's sort of data-driven decomposition, right? But otherwise the story is the same. You have extracted U, and then once you have U's, you can project your data onto these U's and measure the similarity of columns, to each of these U's, okay, to each of these coefficients, okay? So, and therefore, if you have analogy with Fourier transform, if you remember when you have white noise, then all sinusoids have their amplitudes, right? Because it's like white the noise is called white because it's an analogy with the light, but the white light has all frequencies, right? It has all harmonics, basically. It has all colors mixed together, right? The same thing is with the light, with the signal. If it's white, it means that it has all possible sinusoids, all harmonics, all frequencies present in it, okay? And therefore contribution of each of these guys is equal and present and with equal amount, with equal intensity, okay? If you have, for instance, more low frequency components, then the signal is noise called pink noise. This is like pink light, where you have more red spectrum component, which is the slowest one, right? And then you may have the noise which has more high frequency components. I don't know, it's UV or so, I don't know how it's called. But anyway, it will be somehow called but in general it's called pink noise, which means colored noise, okay? So it has certain color to it, so certain frequencies are represented more, okay? But when we talk about the light and when we talk about the signals, we always know what our spectrum tells us about, right? It tells us about the presence of certain harmonic is the key word here, of certain harmonic components, okay? When we talk about the matrices, we don't know what will be the set of basis vectors because it will depend on the data, on the matrix, right? But once we have them, we again can interpret the spectrum of this matrix as the amount with which each of these frames, U1 times V1, U2 times V2, U3 plus V3 is present in your matrix, okay? And from this, you can say that, yes, I see that there are two components, the two main bones, spatial and temporal, present in my data, and but the rest are more or less uniform, okay? Right? So anyway, so that was the intuition. But the only problem here is that if we had this rank 1 data, in rank 1 data was very nice. We have extracted the time series, the main time series, the backbone of the data, right? And we extracted the topography, right? The left singular vector. And then because there was only one guy in the data, of course, they had to be correlated. They have to be pretty much in shape. They had to be equal to G1 and S1, the time series and the topography. Strictly speaking, when you have two-dimensional data, in this case, I mean, two-dimensional meaning that there are two components, but two main components in the data, the singular vectors do not have to be equal to each individual time series or to each individual topography. And you can check this very simply You can, again, this is core coef. You already got used to the fact that core coef measures the cosine, right? So then therefore core coef, let's say UU1 and let's say GI, right? It gives you, see, it's not that exact, right? And if you added more noise, it would be even worse, right? So, and then you can see what about GJ, you know, not this, not that, right? So, and then U2, okay, negative, but doesn't matter that negative, but still slow, right? And then GI, you know. But the good thing is this, look at this. It's close to zero, right? Uh, close to zero. Close to zero. And if I say, if I ask 1 to, let's say 10, no, yeah, let's do it this way. Instead of this cosine, let me plot this multiplied. Let's do transpose here and divide by norm of GI, okay? See, and let's transpose the whole thing. Okay, see, these guys are more or less large, right? Kind of large. And these are very small compared to these two. Okay, the same thing you can do, the same trick you can do with if you let's say v and you match it against s, what was there, si, right? Yeah, match it against si, but you have to make prime here and si. Okay, again the same story for the right singular vectors, kind of correlate with, not really with the first and the second separately, but we kind of correlate with the two of them and almost uncorrelated to the rest of the singular vectors. What does this mean? It means a very simple thing, actually. It means that you found with SVD a two-dimensional subspace where your SI and SJ live, and the same GI and GJ, right? You didn't find individual GI and GJ, of course, because SVT doesn't know about electromagnetic model, nothing. It just got the data. But it found the subspace where your data live, okay? And you can reconstruct your data, right? You can take UU, let's say 1 multiplied by SS, 1 multiplied by VV, 1 plus, let me copy it here, 2 here, 2 here, and 2 here. And I know that I take only 2 because 2 have prominent contributions to the data. The rest is just spread out noise, right? And I call it again X approximated, right? What the, yeah, of course. Yeah, the same mistake as before. Okay? No, why? UU matrix. Of course, I'm stupid, sorry. Yeah, because it's a diagonal matrix, right? You have to, we just have to scale it. So see, the diagonal elements are just simply scaling the contribution of the bones, right? Of your basis, of your you know, your basis vectors that form this main subspace of your data, right? Okay. Then and then we plot XA. See, is it beautiful? So, and then if you compare to the original one, X, and you can get this, and you can get this. Isn't it amazing? Well, you can add more noise, and it will still recover your pretty nice picture. I mean, let's try. Let's say, I will not do more, but let's put 1.5, okay? So F9, okay, and then we do the same story. We have to again do SVD, and then we have to again compute the approximated thing, and then we have to make figure and make plot, and we can make X approximated. No, let's close all for clarity, and then okay. Yeah, I made mistake. Sorry, just a second. Yeah, yeah. But again, the change is dramatic, right? So you cleaned your data quite a bit, right? And the only thing you used is that you know that there is some powerful, there is a set of, in this case, only uh, two, two powerful components that contribute to your data. And these two powerful components have a well-defined spatial and temporal structure. Okay, and you recover this temporal spatial structure, but see, despite the fact that approximation of XA here that comprises these two outer products, right? The scaled outer products, right? This approximation gives you, well, in the noiseless case, it will give you exactly the same data as the original data, but neither U nor V are identical even in shape to G and S. So neither U1, U2, UU1, UU2, and etc. are equal to G1 or GI, GJ. No. But the subspaces formed by vectors UU1 and UU2 and the subspace formed by GI and GJ are very close. Okay. So you estimate not an individual vector, but you estimate the subspace. In one-dimensional case, the subspace is a single line. Therefore, of course, therefore it's only one dimension, and you measure dimension by the correlation of the two. When you are dealing with subspaces, with two-dimensional subspaces, you need to come up with some other measure. Okay, let me show you how we will work with this later. But I will, since I have already this guy shared with you, so I will show you this, right? So if you want to compare the two subspaces, don't disregard the music, disregard data, whatever, disregard. Okay, just the these are the two planes. Okay, imagine high dimensional space, and imagine that you have one plane and then you have another plane. Okay, hyperplanes. Okay, you can think of like a book open in 3D space, or it can be in a hyperdimensional space. It can be. Okay, so what you do, you say that, okay, I have one subspace and I have another subspace. How do I compare if these two subspaces have something in common? Okay, and the subspaces are given to you by the basis vectors. Okay, you can think of, like, in a three-dimensional case, you can think that the first subspace is just one-dimensional, let's say Z axis. Okay, and the second subspace is a two-dimensional space, which is your plane, XY plane. Okay, so the first subspace is given by the basis vector, which is pointing along vector Z, which we usually call K, right? And I and J are the basis, form the basis for the XY plane, right? And then you're asking, okay, how much in common between these two subspaces? And the answer is nothing, right? Well, you know that nothing, right? Because one is orthogonal to the other, right? So how do you formally do it? Well, let's try to find two vectors, one vector in one subspace and the other vector in the other subspace, such that the angle between these two vectors is as small as possible. Okay, so, and you like draw a line basically, right? And then measure this angle, draw a plane and measure this angle. Like here, you found this vector as a linear combination of these two guys, and you found this vector as a linear combination of these two guys, and this angle and this linear combination is adjusted such that this angle is the smallest possible angle, and that tells you the proximity of the two subspaces. Okay, that they have one dimension in common, but how much in common? Well, cosine of theta of gamma in common. Okay, if cosine of gamma is 1, then very much in common, right? If you take a book, right, if you take the three-dimensional space and any two subspaces, which are linear subspaces have to come through 0. So if you have two-dimensional subspaces in a three-dimensional space, they got to intersect. Okay, and they have this will be, let's say, if you take this book, for instance, right? I don't have a book right next to me now, but if you take this guy, right, then this vector will be the common vector for this subspace and for this subspace, right? And this subspace given by these two basis vectors, and this subspace is given by these two basis vectors. Okay, I can combine them with some coefficients from this guy to get this vector, and with another set of coefficients to get this very same vector from these two guys. But then these vectors will align. Ray will be exactly the same, and therefore cosine will be 0. And they will start. I will say that these two-dimensional subspaces have one dimension in common. Okay, and then what I do? Well, then I say, okay, this dimension is in common. Okay, let's forget about it. Let's somehow ignore it. Well, how do we ignore it? Let's take all the vectors. In this case, we have only two basis vectors, right? In this case, and project them orthogonal to this common dimension direction, right? Just, and then you have only planar picture. And let's measure the angle with which left. If we have higher dimensional subspace, we just simply repeat the procedure. But in this case, we will have only two vectors, which are this way, and if these two guys are at 90 degrees, they will have not this, they have the second dimension will not be in common at all. If they are like this, then they will be cosine of this angle in common. If they are like this, they will be cosine this, and if they coincide, then both subspace correlation values, the first one and the second one, will be 1, meaning that the subspaces completely coincide. Okay, completely overlap. Okay, they're identical. Okay, now it's like a spoiler a little bit, but now if you assume that one subspace is coming from your data somehow, and the other subspace is coming from your model somehow, then if you find your data, you can change, you already got them, right? But then if you find the model parameters such that the model subspace and the data subspace coincide, then you can then say that these parameters describe your data. And because these parameters come from the model, from the physical model, they make sense. For instance, they can be location of your sources, they can be orientation of your sources, they can be both, they can be whatever, right? But again, right? So this is the case where you compare the subspaces. And this approach is called music approach. It's called multiple signal. It comes from the multiple signal classification framework in radar theory. Therefore, the title is not informative. I mean, it's just historical. Okay, but this is based on comparison of the subspace, and why you will see maybe by the end of this lecture, or maybe by the end of next lecture, by the middle of the next lecture. But you will see why. But now we will revert back to simpler things. Okay, but always keep in mind this n-dimensional picture, okay, and think about subspaces and try to think abstractly of them, okay? But if you have difficulty, go back to the 3-dimensional world. Everything the same is here, except that it's very difficult to imagine something more than 3 dimensions, okay? And therefore, it's very difficult to imagine two subspaces which are two planes but have nothing in common, okay? Except for 0 element, of course. Okay, so anyway, let me now go back to this beautiful piece of equipment called Samsung Galaxy tab and share it with you, and then we will go.
I have a small, maybe stupid question about
yes, go ahead.
The picture. What is in x-axis there, where we were you were showing us this.
Yeah, let me show you. Let me share the screen again. Yes, sorry. Where is this Zoom? Share screen. Yeah, where? Here?
No,
where?
not here, but in MATLAB graphs. In
here.
Here.
It's just time. It's time. It's your data. This is your data. This is your not noisy data. This is how you see. This is basically how you see your EEG data or MEG data on the monitor in a so-called butterfly plot. Butterfly plot is where each guy is plotted so that the baseline is 0, is common for all time series. Okay, and each color is a single channel time series, and this one is just time. This is the first time sample, second time sample, third time sample, and etc.
So in ordinates we have channels.
Each color is a channel, right? Each color is a channel, and the magnitude here. I think I had this. Hold on, if it has access to it. Yeah, okay. Let me plot this. Let me plot it for you. Okay, so let me plot matter xn, for instance. Okay, all right. So yeah, so see, this is the guy. This is how you got used to seeing the data, right?
Mm-hmm.
So each channel here, each line is a channel. Okay. Now, if you
Mm-hmm.
take the mean lines to the same point, like you somehow snap it, right?
Yes.
And make
Uh-huh,
it
uh-huh.
local by plot. That because to plot this, I simply take each time series and I add some offset, and I
Mm-hmm.
as a matrix basically, and each
Mm-hmm.
offset shows the baseline, the zero line for each of the time series for each of the channels. Okay.
Mm-hmm.
So if you plot them using simply MATLAB plot thing, right? It basically gives you a butterfly plot, right? It plots each column of the data and color codes it. So like
Mm-hmm.
because I plot the transpose, I basically plot each row of this transpose matrix, right, which corresponds to
Mm-hmm.
the
Mm-hmm.
column of
Mm-hmm.
the original matrix. Well, on the contrary, right, I plot the columns of the transpose matrix, which goes to the rows of the original matrix, which are your data, right, your time series. And again, don't forget that there is another way. I plot not the noisy one, I plot the x0, right? There is another way to plot it where you can simply color code it. This probably the most intuitive. Each line is your time series, is your channel
Mm-hmm.
here.
Mm-hmm.
Each row is a channel. Each column is your time instance. That at this time instance, these sensors have low activity, and these sensors have high activity, high amplitude, high positive amplitude. Uh, and yeah, and
Mm-hmm.
that's and you can plot color, or you can put color bar to, you can add color bar to it, and then
So
yeah.
this picture is the picture after SVD, yes?
This is no this one I just plotted. This one I just plotted the not noisy, the not noisy versions. But we can
Ah,
compare if you will we can compare. If you let me do it this way.
yes, I want to have a look at what
Yeah.
will be.
We can have figure. No, we can have it this way. Subplot. Oh, not even this way. Okay, let's plot image scale XA, and then we stick to it the original one, the original time series. Okay, so that they're plotted in the same
Ah,
color
XA,
order.
X approx. Uh-huh, uh-huh.
Yeah.
Yes.
So we see the noise present in the first portion, because this is your noisy data, original one, and I just stuck to it the cleaned matrix, which is
Mm-hmm.
approximated matrix. And because we've chosen only the two components, and these two components are by definition of SVD and by the properties of SVD represent the most powerful component in your data, we highlighted our sources. But of
Mm-hmm.
course, if the noise will be very strong, very, very strong, then the most powerful component will have nothing to do with our sources, and we will
Mm-hmm.
not be able to recover the data. The case would be if we have very strong interference coming. Let's say you have your EEG data and you have eye blinks. And eye
Mm-hmm.
blinks are pretty strong. And if you do SVD on this matrix that have eye blinks, then your first component will be about
Will
eye
be
blinks,
I will, yes.
not
Mm-hmm.
about sources. Okay, but you
Mm-hmm.
can use this property and project your data away from this noisy thing, because this noisy thing will be guys, that they're most powerful ones, they're not what you're
Mm-hmm.
interested in, right? uh but when we process ERP data, evoked response data, because we, by definition, by construction, the ERP data have this reproducible component emphasized, right? Because something which
Mm-hmm.
repeats with the same phase, some phasic response, right? It gets
Mm-hmm.
emphasized, and therefore we know that the sources we are interested in are the strongest, except for maybe the cases when there are some really very bad artifacts, something.
Mm-hmm.
But if there are eye blinks or anything, they don't occur synchronous with the stimuli, right? Typically, if the experiment is designed properly, right? And even if you don't remove the eye blink artifacts after averaging, you have most of the power in the RP due to the sources, and therefore you can denoise, or you can extract what we will call today, hopefully, or maybe next lecture, signal subspace from your data using this SVD kind of thing. Okay.
Mm-hmm. Mm-hmm. Okay, thank
So
you very much.
yeah, thanks for the question. Yeah. So let's go to this slightly simpler stuff now. Share screen, Значит, okay. So yeah, all right. So we have reviewed reviewed the SVD, and it was kind of it was more complicated than the stuff that we are going to be talking now. But now we will be talking with formulas, with expressions, with mathematical language, and they are showed to you with pictures. Okay, so but we will arrive in the end to what I've showed to you with pictures. But first, we will start with some very basic thing. Okay.
But with respect to what is written above, that U is the basis for the column space of A, U consists of eigenvectors of A transpose A. So
Yes.
it's
No. U transpose of eigenvectors of A transpose, and V consists of eigenvectors of A transpose A.
but then how they form the basis for the column space of A itself? It
Because see, very good question. Thank you. See, if I take any matrix A, okay, and I multiply it by any matrix C, okay, my matrix A is, let's say, n by k, okay. My matrix C got to be k by m, right?
Yep.
In this matrix B, which I get as a result, which will be n by m, right? Because these two annihilate, and this is the dimension. The column space of B will first of all be of the same dimension, of course, but I argue that it will be exactly the same as the column space of A. The reason for this is because each column of B is simply a linear combination of columns of A. Because if I write A like this, right, A2, AK with the vectors, okay? And if I multiply it by matrix C, which I will write now, C, let's say C11, this will be simpler, C31, C, what is K, K1, and then C12, C22, and etc., CK2, and etc., right? Then C, in order to get the first element of vector B, I will take the linear combinations of columns of A with these weights, right? With the weights which are columns of which column elements of the column of matrix C, right?
Yes.
And then it, well, right, and then it basically if I take the second element, the same story, right? I will just take second elements of vectors A and combine it with the same coefficients, right? So basically each column of matrix B will be a linear combinations of columns of A. And because the subspace is something closed with respect to the operation of linear combination, right, with respect to A sub I, alpha sub I, right, it will, the span of this guy is if I take for many alphas, right, will be exactly as the span of the original space AI.
So you're saying that column space of A is equal to column space of B, right?
Yes, sure.
But
Yeah.
but if matrix C is not is of rank less than M.
Oh yes. If yeah, of course. If maybe I'm talking about the matrix C that is at least rank is at least K. Yes,
But,
of course.
but at least K. But we need rank M to get.
Yes. If you multiply by matrix, if you multiply A by C, yes. But your original question was about SVD, right? And in SVD we have A transpose, right?
Yes.
And we have U, and in fact, if you know that the rank of the matrix is equal, it's basically you have column rank, you have row rank, but the rank of the matrix is the smallest of these values, right? Therefore,
they equal actually. The row
they're
rank.
equal. Yes. So, well, I mean, it depends on the definition. You can talk. Well, but anyway, yes. Let's say they're equal. Yes. Let's stick to the school. Okay, they're equal, right? And then in this case, your number of non-negative, well, if you say without noise, for instance, right? Non-negative singular values will be equal to this rank. Okay. And then
well,
yes,
but it's gonna happen only if a matrix A is of full rank. But if A is not a full
no,
rank,
if A is not full rank, what I showed to you in the very beginning, you will have one singular value, which will be non-zero, and the other ones will be just simply zeros.
yeah,
And then
that's right. I agree. But then still, the column space would be different. I think if
the column space, yes, with the yeah, very good. We have to correct here, saying that the column space of the, well, okay, see, let me tell you where this whole thing coming from. If you assume matrix A, that is a noisy matrix of your data, which is a full rank matrix, right? Then what I said is correct, okay? Because the column space of A will be given by the column space of U, okay?
okay.
Right? But if A is singular, let's say if it has only one main dimension and the rest are zeros, right? Then in order to approximate the column space, you have to take only the first column of U. And the rest will be living in the orthogonal space, orthogonal complement to this to this column space of A. Okay?
Okay.
And this will be telling you, and which one to take will you will get from the matrix S from its diagonal elements. Because in case of a singular matrix, diagonal elements will be, it will be a matrix, let's say 1.5 and then 0, 0, 0, 0, 0. Okay, if it's rank 2. Okay, but in practice, as I said, you in real life, you always have noise to the data, and you always have non-zero guys here, and it means that you have always some non-zero components along some, like in all dimensions, basically, right? Which in this n-dimensional space where n is n number of sensors, right? But they're insignificant, they're not important to us, and we focus on the subspace. We focus on the subspace that is spanned by the first columns of U, several first columns of U, corresponding to the most powerful singular values. Okay.
Yeah, sure, but still, I don't agree about that U is a column space of A.
Well, it's true. U is a column space of A because okay, okay, let's put it this way. You just yourself said that if C is full rank and everything is good, then it's true, right?
Yeah, in that case, I agree. Yeah, but
Okay,
if it's not
now if all elements of S, all diagonal elements are non-zero, okay? If sorry.
But if all singular values non-zero, isn't that means that A is of full rank? But no, maybe it's not. I don't know.
No, it means that A is full rank. Yes, it means that A is full rank. Yes, but then in general, hold on. So therefore, if A is full rank, then S is full rank, right? And V by definition is full rank because it's orthogonal matrix, right?
Yeah, I agree.
Then everything is good, right? Okay, if A is not full rank, right? Then you will have, let's say it's rank 3, okay? Then you will have only 3 elements of S non-zero on the diagonal,
Yes.
and the rest are 0, okay?
Okay.
And then the column space of A will be the same as the column space of the first 3 elements of U.
Yeah,
okay, that's the main point. That's the main point of this whole thing. Okay, because then if you say that, okay, it's not full rank, but it's like, or it's not full rank, but it's almost not full rank, meaning that there is some noise to it, but it's insignificant. Okay, then estimation of this main subspace, most powerful subspace, the estimate is given to you by the first few columns of U.
Yeah, now I see what you're saying. Like in practical applications, when we have these rapidly decreasing singular values,
exactly,
just letting them go, the most important information concentrated in the first column.
Yes,
okay, I get it. Thank you.
Exactly, very much. But see how it's great to ask questions, right? Because I think not only you understood more, but others understood more, right? And you corrected me because I was not exactly right when saying that column space of A is the same as column space of U. I had to say for full rank matrix, or I had then say only those columns of U that correspond to non-zero diagonal elements of S, right?
Yes.
But that's from you because you come from a different background. You come from maybe more mathematical background, for instance, and I come off like signal processing thing. Okay, and to me, I'm not as strict. Okay, but
Yeah, sure.
okay. So now, again, so let's go back to the to the simpler thing, and assume that we have our data, and assume that we have our rank one matrix, or maybe not rank one, but data plus noise matrix, and that we have some time series x of t that were generated by let's say g some dipole, with some coordinates, g of r, okay, coming corresponding to some radius vector, and with some orientation. Maybe let's assume that the orientation is orthogonal to the cortex, because we know that the dendrites are anatomically orthogonal to the cortex. Okay, and let us say that it's activated with s of t, and let's say that there is some noise to it. Okay, now assume that we are now if you can draw this data, in this kind of butterfly plot, right? They have to come more or less through zero here, right? Because we have a little bit of noise, but because it's sorry, this is incorrect. Yeah, so this has to go. Okay, anyway, somehow this kind of data, right, looks ugly, but you understand what I mean. Okay, now assume that no, this is not what I wanted, you stupid thing. And so assume that you selected some time, some latency. Okay, so this is time. Okay, assume that you selected some t0. Okay, and you want to see, and you want to feed the dipole to your data. Okay, what does this mean to feed dipole to your data? Okay, we all agree, and I think I convince you that the data that we observe with EEG and MEG, they come from activity of what we approximate as like neuronal sources, right? Dendrites, whatever, postsynaptic potentials that we approximate as current dipoles, and that these guys contribute to the data with some topography vectors, and these topography vectors are computed according to some Maxwell equations, whatever, right? So in this very simple scenario, I say that there is only one dipole. Okay, this dipole is located at let's put it R star, okay, at R star location, somewhere in the brain. And if your brain is put in a coordinate system, right, if you put it in a coordinate system, right, then this will be, can you switch off the mic, please? Because it's, yeah, so it will be a radius vector here, R star, right? And our dipole, and this dipole projects on our sensors, right? With these coefficients G, or from this vector, so it will be G1, G2, G3, and etc. Gn, okay, depending on how many sensors we have, and we got the data. Okay, so the data. Now we need to basically, we are interested in the location of the dipole. We are interested in where this dipole is if we see the data like this. Okay, if we see the data like this. Okay, so in this case, because as I said, because we assume that the data are coming from a single source, then I have selected the latency, the time, right? This, okay, which corresponds to the to the largest magnitude. Okay, because, well, it's obvious, right? If I have noise, if I see some large magnitude, and I assume that my data are dominated by the signal, not by the noise, then this thing will probably help me to find the location of the dipole. Okay, and this is not such a imaginary situation, because if we have, like, we do apply the data to, say, interictal spikes of patients, of epilepsy patients. Okay, an interictal spike is usually a very strong, very powerful event. Single trial, basically single spike, it's very powerful, and you can see very nicely the peak of the spike, then the wave, something like this, right? And it's so-called peak wave complex, and you usually feed dipoles to this peak the spike in order to find where the source of this interictal activity is. Okay, and you usually assume, not usually, I mean, but well, often many researchers, many clinicians even assume, but not even many, even researchers, but most clinicians assume that there is a single source behind a spike. Then they may try to look at where the spike goes, and they will try to find the dipole corresponding to this latency in time. This is time to this latency in time, to this latency in time, and then they may see some propagation of activity. And this is something they're also very interested in, okay? But fitting a dipole to one single time slice is assuming that the data come from a single dipole model is not purely academic example, okay? Is not a purely academic example, okay? So let's see how we can do it, okay? So let's hold on. I need to sort my notes. I have them. I have something more beautiful, I think, somewhere. But can of course reproduce it, but I just had nicely structured presentation, but now it's gone. Okay, anyway. We will work with what we have. Yeah. Okay. So yeah. There it is. Yeah, I used it when I was explaining to you the yeah. So this is just to all right. So anyway, we assume that we assume that for simplicity, we just assume that at this time instance, my data, we just fix the data, okay? We just say that our vector X is your data, and they are produced by some activity of my source, A, multiplied by the topography of the source, right? And then you can say that there is some noise, but we will ignore it immediately. So we just place it here. But so again, important. This is the scalar. This is the data that corresponds to the single time slice. Okay, so this is just a vector. Okay, I plotted it with large. I put with large capital letter here. Typically, we have small letters, but let's maybe put a small letter here so that you are not confused. Oops, sorry, no, this is not what I want. Oh, I don't understand how to do it. This is, oh yeah, there we go. Never buy Samsung Galaxy, okay? Okay, X vector, okay? It's A times G plus N. And then you are interested in, and yes, and G, again, depends on R. And you don't know this R, right? You don't know this vector. You know nothing, basically, except that you know your forward model that for any R, you can compute G, okay? G of R, and it'll be the topography, right? So you basically can place a dipole anywhere in the brain and compute the topography, okay? So now, the obvious thing would be, of course, for the rank 1 data is to simply compare the topography generated by the data, by the dipole stemming from each of the locations in the grid, right? Which you can split your cortex into small voxels, right? The small elements, you know, and then you can go over each of them, compute the forward model, or use the forward matrix that you have pre-computed and compare the topography with the topography of the source with your data, right? And then if once you found the location where they're similar, then you can say, yes, bingo, this is where my dipole is. Essentially, this is what we are going to be doing, but we will be doing it a little bit more high-flown way so that we can generalize later. Because what heuristics are good, but heuristics do not allow for generalization usually. You know, if you start something more fundamental, then okay. And let's start more fundamental. Okay, let's say that X minus A G of R, and we want to find such G of R that this thing is minimized. Okay, the norm of this vector. Simply, this is my, if you will, this is my generated model. Okay. This is my generated model, and this is my data, and I want to find the generated model which matches the data. Okay, so this guy is a vector, this guy is a vector. I subtract the two and compute the norm. Why not? This is the measure of how good my generative model described the data. Okay, the thing is that I don't know neither A, neither G. Okay, well, because G depends on R and I don't know the R, right? So, but this is not a big problem because everything is linear and we can make our way nicely around it. Assume that you found some G, which is G of R star, which is good, which is where your source is, right? Then in order to find A, you do this. You say G of R star multiplied by A, right? And plus noise, but we ignore the noise for now, just because we assume that it's everywhere and it's uncorrelated. So this is a vector, this is a vector, right? Then what you do, and let us rewrite it simply G star A, okay. So now it's I can show you the trick how you can do it trivially, but you can, in order to do it formally, you have to do this. You have to again write this functional, and you have to write norm squared of it. Well, you can put also square here, doesn't matter. And you have to minimize it, right? But now you know G star. You know this guy, okay? And all you need to find is you need to find a scalar A, which will scale this G so that it matches X, okay? So it's very simple because if you rewrite this, you can you can rewrite it X minus G star A transpose X minus G star A. Okay, this is exactly the same thing. Then if you can expand it, and you can say X transpose X minus A G star transpose X, right? Then minus X transpose G star A, right? And then plus what is this? A G star transpose G star, right? A. Okay, see, when I was transposing this, because A is a scalar, I didn't transpose it, okay? I just wrote this, right? So, and let's continue. Then you can, this is your functional, and this is something which depends on A, right? And then you have to take the derivative, G of A dA, right? And the derivative of this guy, if you take, so basically you can rewrite it. Let me first write this in a more elegant form. So you have minus 2, because see, these guys are the same, right? Because it's G transpose X and this is X transpose G, and there are vectors and the product is a scalar, and the dot product doesn't depend which vectors you multiply by. You have you can have it this way, is equal to plus, sorry, A G star transpose G star A, okay? And then if you take the derivative of this guy, you get this is a square of A, right? So you basically get 2 G transpose X, okay, is equal to the derivative of this guy will be 2 multiplied by G transpose G star A, right? I understand that you may find it not very intuitive because those are vector quantities, but the thing that you're differentiating with is a scalar, right? Because you simply could have taken the scalar, you could put an A squared here, right? And therefore just take 2, this guy, this is also a scalar, right? So then, and from here you can easily find that A is equal G transpose X divided G star, right? G star transpose G star. Okay, this is trivial thing. This is simple regression problem, but yeah, we solved it in a strict way. Of course, to be very strict, you had to say that now we need to prove that this is actually the minimum. Okay, but because it's a quadratic functional and it's positive, term is positive with respect to a, right? So it's not minus a, but plus a squared. Therefore, it's shaped like this, and it has a single minimum, single extremum point. Therefore, yes. And so you found a star, which is the right. Now, let us take this a star and let us substitute it into this very equation, into this expression that you wanted to minimize, okay, originally. Okay, so it will be x minus g star, okay, multiplied by g transpose x divided by g star transpose g. Okay, agreed? So, and then this is the norm of this guy, which we want to minimize. Okay. The good thing about it is that we didn't really solve the problem yet. We haven't solved the problem yet, but we got rid of a. We assume that we know g, and once we know g, then a will be computed this way, and we simply substitute it. And this is because everything is very simple, linear, and stuff. Therefore, we were able to find the closed form solution for a star. Okay, so we can rewrite this way. Actually, yeah, let's say it's not actually g star, right? It's just g, right? Because we don't know g, right? It basically calls for any g, right? And therefore g times g transpose x divided by g transpose g. Okay, now see, some of you may already see where we are aiming at. Okay, so see, this is a vector, this is a vector, this is a vector, this is a vector. So see, okay, this is g transpose g, which means that you can rewrite it and say that this is this is basically again x minus g multiplied by g transpose x divided by the square norm of g. Agreed? Right? And then let's take the squared norm of g and rewrite this way. Sorry, it's got to be black. G norm of g multiplied by the norm of g. Okay, and let's distribute. Let's combine this norm of g with this guy, and this norm of g with this guy. Okay, and let us call vector b to be a normalized version of vector g. Okay, agreed? So then we can take, well, again, let me put it here, square, right? Then we can rewrite this x minus b multiplied by b transpose x. Agreed? No magic, it's all like trivial. I mean, if you once we arrive, you will be. I just don't do it step by step, so that you can see that there is no magic. But I could have written actually immediately as a result. But anyway, see, we want to minimize this. Let's again rewrite this. Okay. Okay. All right. Now you must already be able to see where I am aiming at. See, in order to minimize this guy, I have to find such a b that this guy is the largest, right? Because I can't change x, I can change only b, and I need to adjust my b such that this whole thing appears to be the largest one. Okay. Now, but b is normalized. It has norm 1. So the norm of this guy doesn't change. The only thing I can change the direction of b, right? The orientation, how it's in this n-dimensional space is oriented. But if you look at what this is simply a scalar product between the unit length vector b, because it's normalized, and normalized vector of your data, right? And that means that it's a cosine between b and x, right? That's where I was aiming at all this time. Okay, and therefore you can rewrite this as x minus b multiplied by cosine of b and x, right? And multiplied by the norm of x. Okay. And therefore, you can reformulate your functional and say that in order to maximize this whole thing, all I need is I need to look for such a vector b that is aligned with vector x, where the angle between the normalized topography vector b, right, normalized topography vector g, but it's b, right, the normalized one, and your data is as small as possible. And that's exactly, in a sense, subspace correlation, but between these one-dimensional subspaces, right? It's on two lines, right? And therefore we can plot theoretically now, and because b is again g of r divided by g of r norm, right? And so you can plot this b, this quantity, you can plot this cosine of b of r and x for each r, and you can find r for which this cosine is maximized, and that will be your start, right? It will be arg max of cosine of b sub r and x. Okay, so it will be argument of the maximum of this function with respect to r. Okay, and r is your radius vector where your data, where your dipole is. Okay, so this guy, right, where your dipole is, this is your r, and you will find it by aligning the data and the model. Okay, and to measure the similarity between the data and the model, you basically use the cosine. And we started from the square difference. We started from the square difference, right? We started from this. Sorry, we started from this guy. We started from this guy, or from this guy. But and then in this one-dimensional case, we demonstrated that it's the same as simply aligning your data with your model, which is one-dimensional model. Okay.